This video is the second part of the lecture, double integrals over general regions, and we're going to solve 3 examples. Example 1 is to solve double integral of x y squared dA over R, where the region R is this. Let me graph it. Let me bring this one a little. So x-axis, y-axis. This is the graph of parabola y equals to x squared. And this is x equals to 2. The region R is here. And this is y equals to 4. So that's the region R. Now, in general, to solve double integral of f of xy dA over R, we need to follow these 3 steps. First, we need to draw the region. Whenever you can, draw the region. And basically, most of the times you can do it because the region R is a 2-dimensional region in xy plane. So we should be able to draw it. The second step is to set up the integral. We can set up the integral of f with respect to dx dy, basically x is first, or we can have it like this, the double integral of f dy dx, okay, over the region R. So we can do dx dy or dy dx. And the third step is to find the bounds. Find the bounds. Okay. So how do we do that? We can do the double integral dy dx. If dy is first, when you want to set up the bounds, you need to consider the fact that in the inner integral, y is changing and x is fixed. X is a constant in the inner integral. And so in that case, all you need to do is to draw a line parallel to y-axis. So when we have dy dx, draw a line parallel to y-axis. When we have dx dy, in that case, since the inner integral has dx, it means that x is changing and y is fixed, y is a constant. So in that case, when you want to set up the bounds, it's good that you draw line parallel to x-axis. Okay, and then you can set up the bounds. So this is the general kind of a procedure of how to set up and basically solve the double integral. But let's apply this procedure to our example. So we have, let me basically move our example down. Okay. And now let's look at the first step. The first step is to draw the region R. We have the region R. Okay, so solution. Let me graph the region R one more time. This is x-axis, y-axis. This is y equals to x squared. This is 2. This is 4. Okay. this is the first step. And the second step is to set up the integral with respect to x first or with respect to y first. Let's do with respect to y first. So we have the double integral of x y squared dy dx. Now I want to find the bounds. When we have dy dx, and this is the similar situation as this one, so we need to draw a line on the region R parallel to the y-axis. So the region R is here, so I'm gonna draw a line like this, okay, with an arrow exactly at the same direction as y-axis. So if you see in here, the first point of the line that I draw in the region R, the first point lies on the curve y equals to x squared. So I'm gonna write the bounds as y equals to x squared. The end point of the line lies on here, and this is y equals to 4. Okay, so y equals to 4. Now, to cover the whole region R, I need to draw the line starting at here and then go up to this point. So on here, I have x equals to 0. And then it goes up to this point, which is x equals to 2. So pay attention that whenever that you're setting up a double integral, the outer bounds, they should be numbers. They cannot be any function with respect to x or y or whatever. They should be numbers. But the inside bounds for the inner integral, they can be functions. Okay? Now that we do it, let's start and solving it. As before, we're gonna write the outer integral and we're gonna solve the inner integral. So it is the double integral of x equals to 0 to x equals to 2. Let me solve the inner integral. This one. This is the integral with respect to y. So x is a constant. So the integral of a constant y squared would be the constant y cubed over 3. And the bounds are y equals to x squared to y equals to 4. And now I have my dx left. Okay, so this is the integral x from 0, x equals to 2. Plug in y equals to 4 in here, so I get x y to the 4, 4 to the 3, which would be 64 over 3, minus plug in y equals to x, plug in x squared for any y that you see here. So it would be x, then x squared to the power of 3 over 3, and then dx. Okay, so what is this one? This is the integral x from 0, x equals to 2. Let's simplify that. It is 64 over 3 times x minus, so this is x squared to the power of 3, so it would be x to the power of 6 times another x, it would be x to the power of 7 over 3 dx. Okay, now the solution for this integral would be 64 over 3 x squared over 2 minus x to the 8 over 8, and I have 1/3 as well in here. So from 0 to x equals to 2. Now plug in 2 for any x in here. So it is 64 2 squared, which is 4 over 6 minus 2 to the power of 8 over 24. Okay. And now minus plug in 0 for any x, so it would be 0 here, another 0 here, so it is 0. So if you solve this integral, you get 32. Very good. This is with respect to y first. Now, let's set up the same integral, but with respect to x first. Or we can say the double integral of x, y squared, now dx, dy. Okay? Let me kind of graph the region one more time. This is y equals to x squared. Is 4 to the region R is here. Now that we have with respect to x first, let's go back to the procedure. X is changing, y is fixed. So we need to draw a line parallel to the x-axis. So I'm going to draw a line parallel to the x-axis. Okay. The first point of the line that I draw lies here. This is x equals to 0. The second point lies on this curve, okay? This curve is y equals to x squared, but I need to have x equals to something into my bounds, okay? X equals to that. So I'm going to solve it for x. I'm basically going to take a square root from both sides. So x equals to square root of y. And now to cover the whole region R, all I need to do is to start at this and then go up, okay? This point is y equals to 0, and I need to go up and draw the lines to cover the whole region R. So it is y equals to 4. That's it. I set up the integral. Now I'm going to solve it. To solve that, I'm going to start with the inner integral. So I will rewrite the outer integral. Okay. For the inner one, what I have is dx. So x is changing, y is fixed, y is a constant. So I have x times a constant. It would be the constant x squared over 2. The bounds are x from 0 to x equals to square root of y. And then dy. Okay, so y equals to 0, y equals to 4. And then I'm going to replace any x with root y in here. So I get y squared root y squared over 2 minus plug in 0 for any x. I get 0 dy. So let me simplify that. 0 to y equals to 4. So I get, this is y, another y squared, y cubed over 2 from y equals to 0 to y equals to, dy. I didn't solve the outer integral, okay? Now I have a constant. I'm gonna write the constant. The integral of y cubed would be y to the 4 over 4, y from 0 to y equals to 4. Now plug in 4 in here. So I get 1 over 8, 4 to the power of 4, minus plug in 0 in here. So I get 0. So this is 4 over 4 divided by 8, which is 32. I get the same result. One of them was dy dx, the other one is dx dy. Okay. These are the solutions for this example. Okay. Let's solve another example. So this is example 2. We have the double integral of from x squared to x, 0 to 1, 1 plus 2y dy dx. So this one is given, but I need to graph the region R first. Always graph the region R. So you see, draw the region R, set up dx dy or dy dx, find the bounds. Okay. So to graph the region, this is x-axis, this is y-axis. How can I graph the region when it is not given? So look at the integral. I have the double integral. The inside one is dy, which means that the bounds that I have in here is y equals to x squared, and it goes to y equals to x. Okay. And then the outer integral is the integral from 0 to 1 dx. So x 0, x equals to 1. Great. So I have all I need. It's y equals to x squared, the parabola. Let me graph it. Y equals to x squared. Then I have y equals to x. So that's the line y equals to x. Okay. And x from 0 to x equals to 1. First of all, what is the intersection in here? It's really important. It's just because we are trying to find the region R. So I need to find the intersection of these two. How do I find this? This is y equals to x squared, y equals to x. Let's set them both equal to each other. To x, don't cancel out. You need to bring everything into one side, and now factor out the x equals to 0. The product of two things, x and x minus 1, is equal to 0. So x equals to 0 or x minus 1 equals to 0, which means that x equals to 1. Okay, so intersection of these two lines is x equals to 0 and x equals to 1. Great. So this is x equals to 0. And this is x equals to 1. Great. That's the region R. You see, x equals to 0 and x equals to 1. Perfect. So the region R is here. Very good. Now I graph the region. I need to set up the bounds. The bounds are like the set up the integral, which is dy dx. Now I need to find the bounds. The bounds are also given. So dy is first, which means that we have a parallel line to the y-axis. From the first point lies here on this curve, which is y equals to x squared. The second point lies on y equals to x. Everything is given, so that's perfect. And now I can graph these lines to cover the whole region R, starting at this point, which is x equals to 0, to that point, which is x equals to 1. Perfect. Let's solve the inner integral first. I'm gonna rewrite that in here. 1 plus 2y dy dx. Okay, so first I'm gonna solve the inner integral. So I'm gonna write the outer integral. And now with respect to y, I'm taking the integral. So the integral of 1 would be just y, plus the integral of 2y would be y squared, from y equals to x squared to y equals to x. And then don't forget the dx for the outer integral. Always write the bounds like this. Y equals to something to y equals to something when you're calculating the double integral or triple integral, because otherwise it would be a little confusing. So I'm going to replace any y with x minus replace any y with x squared. So I'm going to rewrite the outer integral. It would be x plus x squared minus, replace every y with x squared. X squared plus x squared square, which would be x to the fourth. And then dx. So let me simplify that. It would be x plus x squared minus x squared minus x to the 4 dx. These two would be canceled. So I get from 0 to 1, x minus x to the 4 dx. It would be x squared over 2 minus x to the 5 over 5. X from 0 to x equals to 1. So I'm gonna replace any x with 1, 1/2 minus 1/5 minus, replace any x by 0. Okay, so this is the common denominator would be 10, 5 minus 2, which is 3 over 10. This is 3 over 10. Perfect. This is the answer for example 2. Okay, so let's solve the third example. So example 3, which is what? Double integral of the function 1 over y cubed plus 1 dy dx from square root of x to 2, 0 to 4. Okay, first we need to find the region R. Okay, to find that, we're gonna look at here and we see that the inner integral is something with respect to y. Okay, so it would be y equals to square root of x and y equals to 2. And then the outer integral is x from 0 to x equals to 4. Okay, so to graph the region, I need to find the intersection of these two curves. Intersection. Y equals to square root of x and y equals to 2. So I need to set them equal to each other. Make a square of both sides. X equals to 4. So let me graph it. What do I have? Y equals to square root of x. This one. Then y equals to 2. So y equals to 2 is just some line like this. This is y equals to 2. And then x equals to 0 would be here. And then x equals to 4. X equals to 4 is exactly the intersection of these two curves. Okay. This is 4. This is 2. Y-axis, x-axis, and the region R is here. That's the region R. Okay. Now it says that we need to find d with respect to dy's first, which means that we need to find a parallel line. We need to draw a parallel line to the y-axis. And then let's check. The first point lies on the curve y equals to root x. Good. The end point lies on the curve y equals to 2. Good. And then to cover the region R, starting at here, which is x equals to 0, we can graph lines up to x equals to 4. So everything is nice. Now let's start and solve the inner integral. To solve the inner integral, I see that I have y cubed plus 1 and then dy. As you see, it's hard to find, right? So this is hard. How can we solve this type of integral if the with respect to y is hard? We need to change to dx dy. Let's change the order of integration to make it a little simpler. So I'm gonna have the double integral of 1 over y cubed plus 1 dx dy now. Okay, dx dy, and now the bounds are different in that case. Okay, let me, okay, so that was the region R was here. Now that we have dx first, to write the bounds with respect to x, I need to have a parallel line to the x-axis like this. The first point lies and here is x equals to 0. The second point, the end point, lies on this curve, which is y equals to root x, but I need to have x equals to something, right? It's just because we're taking with respect to x first, we have dx inside, so x equals to something to x equals to something. So let me solve for x. I square both sides, so x equals to y squared. And then to find the bounds for y, I consider graphing this line starting at this point and go up to here. So this point is y equals to 0. We go up to this curve, and this curve is y equals to 2. Don't forget, when we want to set up the bounds, the outer bounds should be numbers. So I'm gonna solve the inner integral first. Okay, so let's write the outer integral. Okay, so for the inner integral, as you see, we're taking integral with respect to x, which means that all the y's are constant. So this expression in here is just a number, it's just a constant, because we are taking the integral with respect to x. So the integral of a constant dx would be the constant, which is this one, times x, right? And then it is from 0 to x equals to y squared. Very good. So gonna rewrite the bounds, replace any x by y squared, y cubed plus 1, minus replace any x with x, which is with 0, which is 0. Okay, and then dy. Now I need to solve this integral. It is not familiar, so we need to use u sub. We're gonna use u sub. I need to take something as u. As you see, whenever that we have a fraction, it's better to use denominator as your u. So u is y cubed plus 1 du would be derivative of that 3y squared dy. Okay, so replace everything. I'm not gonna change the bounds. I'm just gonna keep the bounds and rewrite everything, solve the integral, and then after that I replace u with the function, I'm gonna use the bounds. So denominator is u. Then I have y squared du. Y squared du is y squared dy is 1/3 du, and so 1/3 is just the number. The integral of du over u, which is the number ln of absolute value of u. Now replace u with the function, which was this function, y cubed plus 1. Don't forget the bounds. Now let's look at the pounds. Now that everything is with respect to y, I can use the pounds. Y 0, y equals to 2. So it is 1/3 ln of 2 cubed, which is 8 plus 1 is 9, absolute value of 9, minus 1/3 ln of 0 plus 1, which is ln of 1. ln of 1 is 0. So ln of absolute value of 9 is just ln of 9. Great, that's the answer for this integral, which was hard at the beginning. So I changed the order of integration. The bounds changed. As you see here was root x to 2, 0 to 4, but here is 0 to y squared, 0 to 2. And then I was able to solve it. Okay, great. Thank you, everyone.